uh, pardon. Okay, let omega be the set of all real numbers. Okay, and A the countable subset of reals, which is the set of integers. Or maybe let me just choose the set of positive real numbers. Okay, positive real numbers. And so this is just 1, 2, 3, and so on. And let P be the measure on this subset defined by this. Okay, so the measure of 1 over n squared is sorry, measure of the singleton is 1 over n squared. So whenever you have a subset, so whenever if let's say B is a subset of R, then the measure of B will be what? Just the measure of B intersected with the set of positive integers. Okay, you look at the positive integers contained in B, and you just compute 1 over n's and add them up. Maybe I should be a little bit more careful because this measure is not a probability measure. The measure of all integers, positive integers, is not 1, right? It is the sum of 1 over n squared, and sum of 1 over n squared is, I guess, pi squared over 6, right? So maybe I should be more careful. This should be divided by pi squared over 6. Okay, so that hence the measure of the set of all real numbers. This is the measure of real numbers intersected with n, and this is the measure of all positive integers, and this is just so 1 over pi squared over 6 times the measure of each integer, and that is just pi squared over 6, and this is 1 over n squared from 1 to infinity. Well, this summation is just pi squared over 6, pi squared over 6, so this is 1. Okay, so this is, for example, an example of discrete probability. Although your, you know, sample space is uncountable, only a countable subset of elements have non-negative, positive measures. All other subsets or elements have measure 0, right? Here our algebra is the set of all subsets. Okay, so our algebra is the power set of R, which is an huge set, but among those only the ones which contains natural numbers has a positive measure, and their measure is defined this way. You just look at the integers contained in that set. For each integer, you take 1 over n squared, you sum them up and divide that number by pi squared over 6, so that the the total space has measure 1. Okay, this is an example of a discrete probability space. We have other probability spaces, for example, geometric spaces. Let me explain them. geometric probabilities. All right, now consider Rn together with its Borel sigma algebra. What was Borel algebra? It is the algebra generated by all open subsets. Since algebras are closed under completion, it is also the algebra generated by all closed subsets. Okay, and we consider and that algebra again with its Lebesgue measure. Lebesgue measure. This is not a probability actually, because the measure of all Rn is infinite, right? It is not a finite algebra. However, you know, on some subsets we may define it as a probability as follows. So let G, for example, be a subset, be a Borel set. Borel set. So it's a element of the algebra with finite Lebesgue measure. Uh, let me denote it like this: measure of G. So G is a subset whose measure is finite. G may not be finite, but its measure is finite. Okay. Let A be the set of all Borel sets, subsets of G, and define P on A as follows. So I define the measure of A as what? We take its Lebesgue measure and divide it by the Lebesgue measure of the whole set G. Okay, for any A of the algebra, for any event in the algebra. I will leave as an exercise. Check that this is a probability measure on A. Well, let's see an example. Once you see the example, you will see that proving this will be something really easy. Problem of meeting. Let me describe you the problem. So two people agreed to meet between, let's say, 12 a.m. and 3 p.m. and they agreed on the following. They come to the place where they will meet at random. Okay. The condition on this meeting problem is the first coming person waits for an hour, for 1 hour, and then goes away. Okay. So the question is, what is the probability of meeting? Okay. Uh, is it understood what the problem is? So how can we solve this? Well, our sample space is the set of pairs x and y, where x and y are the possible uh, times each person will come to the place. So this is a pair of real numbers, so that both of them are uh, non-negative, and they show the time possible times where these uh, persons will come to the place. First person will come, let's say, at uh, x o'clock, and the other one will come to the place at y o'clock. And let omega, sorry, a to be the following subset. So these are elements of the sample space, so that the difference between the times these persons will arrive to the place is less than 1 hour. Okay. So then what is asked is the, you know, uh, measure of a compared to the measure of omega, right? How big a is inside omega. That's what we are asked. Then we are asked PA, which is just the measure of A divided by measure of omega. Let's compute these. We are talking about Lebesgue measure, and Lebesgue measure is basically the area, right? Area of the region. And here, in this case, it is easy to compute these areas. So first, okay, this is, let's say, xy plane, and let's say this is 3 by 3, our omega, and here, let's say, so this is 1, 2, 3, and 1, 2, 3, and the region A is what? It is the set of all points where x and y is less than 1. Well, x minus y in absolute value equals 1 means x minus y, is less than 1 means x plus y is between 1 and minus 1. Okay, so this means y is between ya da şunu y minus x diye de yazabiliriz. Is less than 1 plus x and larger than x minus 1. And it corresponds to the following. So this is one of the lines. This is the second line. And A is this region. Okay. This line is, so this one is y equals x minus 1, right? And this one is y equals x plus 1. So Yani isterseniz buraya tekrar yazayım. X minus y is less than 1 if and only if y minus x is between 1 and minus 1, and this is if and only if y is between 1 plus x and x minus 1. So what is this measure then? Well, area of A is how much? Şuradan, so if you cut like this and this, yeah, this is evet, bu üçgenleri çıkartsak daha kolay olacak. Okay, so the total area is 9, and I have two triangles here whose sides are 2 and 2. Actually, the sum of these two is just, right, this region and this region is a square of side length is 2. So total area of this triangles is 4. Total area of the big square is 9. So the area of A is 5, right? This is 5 divided by 9. So the probability is 5 over 9. It is larger than 50%, right? Sorusu olan var mı? Any questions so far? Okay. Let me give you an exercise. Again, a geometric one. Suppose you have a set of parallel lines in the plane like this. Okay. And the distance between any two of them is, let's say, 2 units. Okay, 2 units. And you have a needle, let's say, of length 1 unit. Okay, let's say, all right, so 1 unit, 1 unit length needle. What you do, you throw this needle in the air, it will fall, and it will either, lie something like this, it will not touch any line, or sometimes it will touch the line. Okay, so what is the probability that the needle will touch one of these lines? Think about this. Okay, compute the probability that a needle thrown into the air will touch one of the lines on the ground. Okay. Think about this. Okay. If you cannot come up with an answer, we can discuss it later. All right. Section 1.4 is so-called conditional probability and independence. Conditional probability and independence. Okay, so let, as usual, omega a p be a probability space, be a probability space. Uh, Fixed once and for all. So in this subsection, we will we have fixed probability space. Now we will see some definitions. First of all, uh, definition of conditional probability. Let's see what is this. Let A and B be two events in A such that the probability of the event A is positive. Okay. Then the conditional probability, then the conditional probability of B occurring under the condition the condition that A is known to have occurred. Or another name for this, or the uh, conditional probability of B given A, denoted by P B A. This will be notation, is defined by the following formula, is defined by, so the probability of A, sorry, B given A is the uh, probability of the intersection divided by the probability of A. Okay, so this is the conditional probability. Okay, conditional probability of B under the condition that A is known to have occurred. Okay, now there are some remarks. First one is the following. In measure theory, uh, as a function of B, the expression P A intersection B. So A is fixed. I am changing B. So I consider this thing as a function of B. This is called the restriction restriction of the probability measure to the subset A, and this number is called the normalized restriction. Why normalized? Because since, let me just say it this way, what is the measure of A? Well, this is by definition, it will be just okay. So since for B equals A, we have A intersection A divided by the measure of A. So this is the measure of A divided by measure of A, which is 1. That's why we call it normalized. So in the measure space, original measure space, the measure of A may not be 1, right? It is probably some positive number, but not necessarily 1. We normalize it by just dividing this measure by the constant, the measure of A, so that the measure of A now becomes 1. Okay. In other words, we restrict our space, sample space, from omega to A. Okay. So that A becomes itself a measure space, a probability space. And for that to be a probability space, of course, to the total measure of A should be 1. So you rescale the original measure so that the measure of A becomes 1. All right. The second remark is this. If the measure of A is 0, then we will just define this to be defined to be 0 for all B. This is something reasonable. Why is that? What is this thing? This is the probability of B given that A have occurred. But since its measure is 0, A will never occur. Okay. Therefore, this thing should have probability measure 0 also, because A will never occur. Therefore, B will not occur under the condition that A have occurred. Okay. That's why we define this gadget to be 0 if A has measure 0. Efendim? Haklısın. So we should write it this way. Okay. Değil mi? Yes. Yeah, probably I will write it in the wrong order. I mean, this will not be the last time I will write it this way, so be awake about that. Okay. Let's see one more example. So let omega A P be the mathematical model model of tossing a die. Suppose we are in the classical scheme. Therefore, each face of the die will have the probability 1 over 6 because it has 6 faces if it's a cube, right? Then if it is given that an even number occurred on the die, what is the probability to have S6 what is the probability to have F5? Okay. So, what is A? We are given that an even number occurred on the die, right? So, we take A to be the possible even numbers on the die. B is 6 and C is 5. Well, what is the probability B given A? Well, this is just the probability of A intersection B divided by A. Well, A intersection B is just 6. So this is P and this is A. Okay, this is just 1 over 6. And this is, it has 3 elements. So it is 3 times 1 over 6. So it is just 1 over 3. Okay. Since this has A has 3 elements, the probability of A is 3 times 1 over 6. Okay. We are in the classical scheme. Therefore, each element of omega has equal probability. Therefore, each one has probability 1 over 6. What about the other conditional probability? A given C. Well, this is by definition intersection of C and A divided by A. C and A, well, that is the empty set, right? That's the empty set because 5 is not an even number. And the probability of empty set is, of course, 0 divided by 1 over 2. So this is just 0. Okay? All right. Okay. Properties. Sorusu olan var mı? Any questions so far? You know, if there's anything you don't understand, just stop me and ask, okay? Probabilities of the conditional probability. Okay, first, this function, so uh, the first slot is for the subset you put to measure the probability. This is considered as a function on the algebra A. Uh, oops. Of course, it will take real numbers, values. Is also a probability measure on A. Well, it has to satisfy the, of course, axioms. What are they? The measure of omega, right, should be 1. Well, what is this? This is the measure of omega intersection A with the divided by the measure of or probability of A. Well, omega is the whole set. Therefore, this is just PA divided by PA, and this is just 1. Second, it has to be non-negative for all B in A, P, B, A. What is this? This is probability of the intersection divided by the probability of A, but they are all non-negative. Therefore, this ratio is also non-negative. And the third one, uh, if let's say Bn is a countable collection of mutually disjoint events in A, then the probability of the union should be the sum of the probabilities, right? Let's see if it is the case. The union, okay, sorry, and from, let's say, 1 to infinity. What is this? Well, this is by definition P of the union intersection with A, right? And from 1 to infinity divided by A, probability of A. Well, what is this? This is just P of the unions from 1 to infinity B n intersection A divided by P of A. Well, here Bn's are mutually disjoint. So since Bn intersection Bm is empty if m is different than n, so is, right, Bn intersection A intersection Bm intersection A, right? This is also empty, and hence, since P is a probability measure, measure of a disjoint countable union is equal to following. We have, so this gadget intersection A is equal to, well, the numerator can be written like this. divided by A. And this is, of course, equal to what? This is just, I can write it this way, and from 1 to infinity, P of Bn intersection A divided by this. Right, this is a fixed number, positive number. I can take it inside the summation. And what is this gadget? Well, this is just, and from 1 to infinity, this thing is just P of Bn given A. So we have shown then that, you know, yok şöyleydi bu. Okay. This probability is given as the sum of the probabilities. The second property is that PAA is 1, of course. What is this? The probability of A given A. Right? This is just by definition is equal to this. And this is PA divided by PA. So this is just 1. Third one, if A and B are disjoint events, in other words, A intersection B is empty, okay? So these are disjoint subsets of the sample space. Then, of course, the probability of B given A should be 0, right? They cannot occur at the same time. Then P B given A, what is this? This is by definition the measure of the intersection divided by the measure of A. But this is the empty set, therefore this is 0. And the final property I will list is this. Probability of B complement given A. What is this? Well, this is by definition B complement intersection A divided by A, probability of A. And this gadget here can be written as P of A intersection A union B. Intersection A. Right? A intersection complement of A is what? You just subtract from A uh, the intersection of A and B, right? You take complement of B and intersect with A. That is, you just subtract from A the intersection of A and B. And what is this? Well, okay, so this is şöyle yazmışım ama this is 1 minus okay. Bir dakika. Böyle yazmışım ama şimdi göremiyorum. Bu o zaman çok bariz gelmiş muhtemelen. Uh, hmm. Ee, ama yukarısı şeydi ki disjoint union neyin disjoint union'u? A minus A intersection B. Ee, bir dakika. A'dan bunu çıkartırsak yani bu basit bir şey olması lazım ama şimdi kafam karıştı. Okay. Well, all right. Let me just think about this, and you also think about this. So this should be true, but I don't see how we pass from this line to this line. What is this? This is just this gadget is equal to probability of A intersection B and PA, right? A intersection B. Okay, I think we should write it this way. This is A intersection B union A minus, okay, B or A intersection B de olur. Okay. So PA, this is disjoint union. Therefore, PA is just PA intersection B plus PA minus A, şurası intersection. Evet, şöyle. O zaman da ne elde ediyoruz? Bunu PA'ye bölersek 1 and this is PA A intersection B. Yes. And therefore this thing is equal to 1 minus this gadget. And what is this? This is just P B given A. So this is just, yeah, okay. So yeah, we are done then, right? Okay. So yani okay, this is true. Proof is this. Okay. All right. Sorusu olan var mı? Any questions so far? All right. So on Thursday, I'll continue from this point. All right.